In this video, let's take a look at example 1 and see how we can actually use the theorem that we talked about in the previous videos to find the arc length for a specific function. So here we want to try to find the arc length of the r of t that's given, specifically from one point to this other point. So one of the things that I like to do kind of right away with certain examples like this, especially when I'm first introduced to this topic, is I want to take a look at the picture of this vector function and also get an idea of what is the portion of the curve that I'm working with. Okay, so let's go over to the 3D grapher and set this up. Okay, over here at the 3D grapher, I can see a couple things going on. First off here, I can see that I have this kind of helix-shaped sort of vector function here. It seems like it's spiraling around. And you can also see that I've plotted on here the 2 points. You can see one of them up here and the other down here. This one appears to be the one that has the higher z-coordinate. And this one down here is the 1, 0, 0. Okay, so I'm interested in the portion of the curve that exists between those 2 points. But I should notice something then right away when it comes to the actual calculation. I'm going to need to figure out exactly what values of t I'm going to need. Because remember, when I set up my integral, I need to integrate from a value a to a value b, and those are t values. So I need to know at what time does my actual vector function reach this point 1, 0, 0, and at what time does it reach this other point. So let's go back to the notes to try to take a look at exactly when this is going to occur. Okay, so we need to try to figure out when does my vector function here arrive at the point 1, 0, 0. Well, this should be pretty easy to determine because I need the cosine to spit out the value of 1, the sine function to spit out the value of 0, and here's the dead giveaway, I need the z-coordinate, which was determined by t, to also spit out 0. So I can state here that clearly 1, 0, 0 is reached when t is equal to 0. And I can double check that it's going to work for the other coordinates. Sine of 0 spits out 0, cosine of 0 spits out 1. But I can also see that negative 1, 0, pi over 2 therefore has to be reached when t is equal to pi over 2. Oops. Let me just make some extra space here. So this is when t equals pi over 2. Okay, so this is clearly what I'm working with here. And if I was to go back to the 3D grapher and take a look, adjust my values of t, I should be able to see this. So let's switch back over again really quick. Okay, so over here at the grapher, you can see if I go to my values of t, if I change this to be 0, and then I also change the next one here to be pi divided by 2, boom, there it is. I should only get the portion of the curve that exists between those 2 points. That's pretty awesome. Okay, so now that I know my starting and stopping points, let's check the conditions that we need in order to make sure that we can use this theorem. All right, so let's go ahead and scroll back up here and refresh on what those conditions are. Remember, I needed to have my vector function be smooth, meaning that it needs to have a continuous first derivative that is never equal to the 0 vector for any t. And it also has to be the case that the curve is traversed only one time. Well, I think it's pretty obvious from the graph that we looked at that the curve is only traversed one time. It went from the low point to the high point, so that's really not an issue. But we do need to check this idea of smooth. All right, so let's go ahead and calculate what my r prime is. So I'll say note r prime of t. Let's try to write this out here. Well, I'm going to need to take the derivative, remember, of each of my component functions. So this should get me negative sine of 2t, but then times 2 from a chain rule. Similarly, a cosine of 2t, then times 2 from a chain rule. And the final component would just be a 1. Okay, now I can double check a couple things here. First, are each of my individual components continuous? Absolutely. I have some nice simple trig functions that I know don't have any horizontal or vertical asymptotes or anything weird like that happening on them. Nice continuous functions. And I can also guarantee that my r prime of 0 or r prime of t is never going to be equal to the 0 vector. Because, well, I mean, the z component is 1 all the time, so there's no way that all the components can ever hit 0. Okay, so I'll say here again that clearly r prime of t is continuous, and r prime of t does not equal the 0 vector for any t, so r of t is smooth. Okay, I have to check that condition. I have to actually write that check out in my work. I should also add here that r of t traces the curve only once on t equals 0 to t equals pi over 2. Okay, so both conditions are met, and so now I know that the desired length will be given by an integral of the norm of r prime of t on the interval from 0 to pi over 2. So notice here, if I go ahead and I actually attempt to set up what this integral fully looked like, I would just have to compute the norm of that r prime that I already have listed up above. So remember, that means I'm going to have to square each of my individual components. Notice that if I do that here, I'm going to get like 4 sine squared of 2t plus 4, not a sine, 4 cosine squared of 2t and plus 1 squared, or just plus 1. But fortunately, this actually simplifies up pretty simply here, because if I have a cosine squared plus a sine squared, that should always be equal to 1, right? That's one of my favorite trig identities. And here I just have 4 sine squareds and 4 cosine squareds. And so those should just add up to a grand total of 4. And therefore, I really just have a square root of 5. So my antiderivative is going to be square root of 5 times t, evaluated from 0 to pi over 2. And so, of course, I just get square root of 5 times a pi over 2 once I evaluate. And this right here would represent the length of that curve that I had in the graph. So that's the way that I would actually go about doing this sort of calculation. Now, it may not always be the case that your integral simplifies up this nicely, and on occasion you should just, or I might just ask you to set up the integral and not bother evaluating it. Every so often I may ask you to evaluate it. It would just depend on what the question asks.